A very typical sort of problem is called Le Chatelier's principle. And the idea is if there is a system at equilibrium, then if you make a change to that system, it will shift in a way that will kind of undo the stress you put on that system. So we talk about stresses, and stresses is you have too much of something or not enough of something. And we could be talking about a chemical, so maybe you add some chemical or take some chemical away. It could be you heat it up or cool it off, and that would be too much or not enough heat. Or you could have too much space or too much pressure. So if you were to decrease the volume, that would squeeze the chemicals and they would shift to kind of maintain its equilibrium. We should get to the point where you can predict what sort of shift and what's going to happen to each of the chemicals in the equation. Now, somewhere halfway through, we're going to make a distinction between the amount and the concentration, and those two ideas have slightly different answers because of the idea that you cannot change the concentration of a liquid or solid, so it only affects liquids or solids. You're also going to see some problems where they say, okay, let's add a catalyst, and if you add a catalyst, the answer is it does not shift the equilibrium. You get to the exact same equilibrium, you just get there faster. And it's because you're going to speed up the forward and reverse reaction by lowering the activation energy. Putting in an inert gas, let's say you pump a bunch of helium in, you pump a bunch of argon in, something like that, that will be kind of the same as a catalyst. You get to the same exact equilibrium, only this time you get there more slowly. So if you wanted to try to slow down a reaction for some reason, you could surround it with an inert gas. And then the final thing is we want to kind of pull this stuff all together, and you get something called the Haber process. And the Haber process, very, very important way to make ammonia. So we're going to utilize the information that we've learned by these problems about Le Chatelier's principle, and also ideas we learned from the kinetics chapter, and put it together for the Haber process. The guy here in the corner, that is Henri Louis Le Chatelier. Now, the steps we're going to go through to solve these problems, and I really find that this works nicely for doing these kind of problems, is first you need to identify the stress, okay, and that just means there's too much of something or not enough of something, and it could be too much of a chemical, okay, or not enough of that chemical. There could be too much pressure or not enough pressure, or that could also be translated as too much room, not enough room. And the last thing is temperature, so there could be too much heat in the reaction or not enough heat. Once we get that step, then we're going to say, okay, which direction will the system shift? And so right below the double arrow in the equation, I usually write a little scoopy arrow and say I think it's going to shift to the right, or I think it's going to shift to the left. Now, even doing multiple choice problems, I usually translate my problem into is it shifting to the right or shifting to the left? That's a really useful idea. Then we're going to find out that if we're adding or removing chemicals, that chemical actually acts a little different than the other chemicals. So I put that one in first. So anything you add goes up, anything you remove goes down. And then all the other arrows according to the scoopy arrow. So we're saying if I said something shifted to the right, then anything on the product side is going up. Anything on the reactant side is going down. So I do it those steps. Identify the stress, determine which way it's going to shift, draw in the first arrow, and then do all the other arrows. Now I'm going to try one example and going through my steps for this, and then after that I'm going to ask you to try the problems and don't run the program. So pause the program, try the problems, and then watch the answer. So here's my example, and this is actually the one we're going to be looking at later on when we do the Haber process. So nitrogen gas, hydrogen gas turns into ammonia gas, and the fact they're all gases, that's kind of an important piece, and we'll see that as we go. So we're going to say, I'm going to add some N2 gas. So my stress, I've got too much N2 gas. And what do I mean by too much N2? Is that right now is implied, because we have our double arrow, that this is in equilibrium. It's all balanced. So if I add some N2, now there's too much N2, okay, to keep that same balance. So which way would it shift? Okay, let me kind of clean up my page here. It's going to shift to the right. because if I have too much N2, it's going to shift to the right. That'll use up some of my N2. Okay, now I'm going to go through and say what happens to my first arrow. My first arrow is my N2. Because I've added it, it's going to go up. Now, even though I'm shifting to the right, and shifting to the right means I'm going to use up these two chemicals, and I'm going to make some of this chemical, well, even though I've used up some of this chemical, I added it. And it turns out that it reaches a new balance before it has a chance to use up everything I added. So my net change here is always going to be up. So whatever I add, the net change is going to be up. Whatever I take away, the net change will be down on that. Let's erase this extra stuff. Oops. Now, because I'm shifting to the right, I'm going to say my products are going to go up. So this goes up, and my reactants are going down. Whatever's on the front side of my shifty arrow, my scoopy arrow, is up, and whatever's on the back side of my shifty arrow is going down. Okay, let's try the second one. I'm going to add some NH3. There's stresses that there's too much NH3, so I know it's going to shift to the left. So this is my first two steps. Identify the stress, figure out which way it's going to shift. Now I'm adding NH3, so I know that goes up. Now, because it's shifting to the left, I know these others, my reactants here, are also going to go up. So that's how this is done. Let's try another one. Remove some H2. My stress is that there's not enough H2. So I'm going to shift to the left, and that'll kind of remake some of my H2. Second step, I'm going to remove H2, so I'm taking that down. And now the other two arrows follow my shift arrow, and the scoopy arrow says this guy goes down, and the front side of it goes up. So I end up with up, down, down. Now, if I increase the volume, that is going to have a different effect. And we're going to go back and say, okay, if I increase the volume, there's too much room. Now, if there wasn't enough room, we would try to shift to whichever side takes less room. And since they're increasing the volume, we're going to shift to whichever side takes more room. Now we have 4 moles of gas on the left side of the equation, 2 moles of gas on the right side of the equation. Now we know at the same temperature and pressure, each mole of gas takes up the same amount of room. So we're saying that this product over here is going to take up this much room, and the reactants over here are going to take up twice as much room. So if I have lots of room, in fact too much room, the reaction is going to shift to the side that takes more room. Now to me, it makes more sense if I think of the backward situation. If I didn't have enough room, if I had too small a volume, and I could do that by increasing the pressure, then shifting to the side that takes less room would make more sense. But here, as the opposite, I have too much room, so I'm going to shift to the side where it has more moles of gas, and that will help alleviate the stress. So I'm shifting to the left. I have too much room, so now I don't have to worry about that first arrow because I'm not adding or removing anything. My arrows all follow my shifty arrow, so this guy on the back goes down, and the two in the front of my arrow go up. So if I were to increase my volume, it would shift my reaction to the left. Final one here is increasing my temperature, and if I increase the temperature, I just think of heat as one of my reactants, and I've got too much heat. So which way can this reaction shift to undo that? Well, it actually shifts off to the left, because the reverse reaction would be counting as an endothermic reaction. That would require some heat, so that would use up some of my excess heat. And again, since it's shifting to the left, it's going to be up, up, and down. So the arrows on the front side of my arrow go up, and the ones on the back side of my scoopy arrow go down. So again, if I'm adding or removing chemicals, I have that extra step of putting up for anything that goes up, anything I've added, down for anything I've removed. But if I'm increasing the volume, I just shift whichever side takes more room. So I go by moles of gas. And again, if there's moles of liquids or moles of solids, their volume doesn't change, so don't count those. Only moles of gas when you're doing volume. And temperature, just do the heat part. And you need to be told here somehow, where the heat is. So it might be a situation where it just says the delta H is positive, and if that's the case, the heat's on the left side of the equation. Or in this case, it might have said that the delta H is some kind of a negative value, so you know that the heat's on the right side. Okay, so what I'd like you to do is to try problem 1, pause it right now, and then I will go over the answer. For A, addition of PCl3, there's too much PCl3, so it's going to shift to the right. Because I've added this, this goes up. Now the other two follow the arrow, so this goes down, this goes up. Removal of Cl2. I don't have enough Cl2, so we're going to shift to the left to make more of that. Because I removed the Cl2, its number goes down, its amount goes down, and the other two follow my scoopy arrow, so the backside is there and this guy is up. Removal of PCl5, that's the one on the right. Okay, if I remove it, there's not enough PCl5, we're going to shift to the right to make up for it. Because we remove it, this goes down, but the other two follow the scoopy arrow, so they're down, so it's down, down, down. Now I decrease the volume of the container. There's not enough room. So this side has 2 moles of gas. No, it doesn't. Okay, this side has 1 mole of gas. This side has 2 moles of gas. So if I don't have enough room, we're going to shift to the side that takes less room. So we're shifting to the right, and all of my arrows just follow my scoopy arrow, so it's down, down, up, and that's the answer. Again, problem 2, press pause, try the answer. If I add some CO2, there's too much CO2, so we're going to shift to the right. Because I added the CO2, this one goes up. Now the other 3 are going to follow my scoopy arrow. So on the back side of my scoopy arrow, that goes down, this goes up, and this goes up. We don't usually put a value for the heat. Okay, addition of a catalyst. Remember we said a catalyst, as soon as you see that, say everybody is dash, 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 dash. We get to the same equilibrium, we just get there faster. Increase in temperature. Increase in temperature, too much heat, so we're going to shift away from the heat. Now everything follows the scoopy arrow, so the front side of the scoopy arrow is up, back side of the scoopy arrow is down. And decrease in the volume of the container, so on the left side of the reaction there are 2 moles of gas, and on the right side of the reaction there are also 2 moles of gas. So there is no way to shift to undo this stress or reduce the stress, so in this case there's no change all the way across. Problem 3, same thing. Go ahead and try this problem, press pause, and then I'll go through the answer. If we add some N2O, there's too much N2O, so we will shift to the right. Because we added the N2O, we're going to make that go up. But the other 2 are going to follow the scoopy arrow, so that's down and that's up. Second, I remove some O2. If we remove the O2, we're going to shift to the left. The chemical removed goes down, but the other 2 arrows follow the scoopy arrow, so it looks like that. If we increase the volume, okay, so let's look at moles of gas. On this side, on the left side, reactant side, we have 3 moles of gas. On this side, we have 4 moles of gas. So if I have too much room, we want to shift to the side that takes more room. So we're going to be shifting to the right. And everybody follows the scoopy arrow. So it's down, down, and up. And finally, if we add a catalyst, no change. We get to the same equilibrium, just more quickly. Okay, a very important point here, that if the question says amount, you get a slightly different answer than if it says concentration. So watch for this very, very carefully, whether it talks about amount or concentration. And in the 3 problems we've already done, we're talking about what's the amount, and what's the amount. So we've been doing exactly right so far. But the idea is, concentration is moles per liter. And we were talking earlier in another tutorial that, let's say we were talking about a liter of water. you can calculate the concentration of that liter of water, but there's nothing you can do except change the temperature. There's nothing you can normally do to get more water into that liter of water. So for a solid and a liquid, the concentration cannot change. It always stays the same. So if you see a problem where it has a solid or a liquid in the equation, if it says which way is it shifting, just mark it dash, because its concentration cannot change. The amount could change. So if you, the amount of liquid could go up, the amount of liquid go down, same with solid, but the concentration will not change. So if you see solid or liquid and it's asking concentration, you can just put a dash before you do anything else. So here we are, problem 4. Now notice that we do have a liquid in this equation. Go ahead and try this, and then we'll come back and we'll solve it together. Adding O2 to the system. Too much O2, so we'll shift to the right. Because we added the O2, it goes up, and the others follow this arrow, or scoopy arrow. But here we have liquid, so even though the amount of that goes up, its concentration is not going to change. Now, we can go ahead and do this on all of these right now before we forget, because it doesn't matter what you do, its concentration cannot change. Adding N2 to the system, there's too much N2, it'll shift this way. Because we added it, it goes up, and the others follow the scoopy arrow, so it's up, 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 no change. Removing H2O from the system. Okay, we're taking away H2O. Oh, okay, but since we're removing something whose concentration doesn't change, then that has no effect on the equilibrium. So adding or removing a liquid will not shift the equilibrium because it cannot change its concentration. And the last one again is decreasing the volume of the container. Now when we do moles, we only count moles of gas because that's the only thing that can change with the volume of the container. So on the left side, the reactant side, we have 7 moles of gas, but on the right side, even though there are 8 moles, there's only 2 moles of gas. So decreasing the volume is going to make it shift to the side with fewer moles of gas. So we are going to shift to the right. And our arrows just follow the scoopy arrow, so it's down, down, and up. You can see how that last one will be a little tricky. Only look at moles of gas. Try number 5, press pause, and then come back and we will do the answer together. Adding CaCO3 to the system. Okay, adding CaCO3, because it's a solid, it will have no effect on the equilibrium. And also we can go down right now and say these are solids, so their concentrations are not going to be changing. Okay, number 2, letter B, adding CO2 to the system. Okay, too much CO2, it's going to make it shift to the left. So because we're adding this, this goes up. Even though it shifts to the left, we know whatever we add goes up. Removing CaO from the system. Again, CaO is a solid, so changing it will not change its concentration, so it has no effect on the equilibrium. Decreasing the volume of the container. Okay, this side on the left has 0 moles of gas, where the right side has 1 mole of gas. So if we decrease the volume, the stress is we don't have enough room, so we're going to shift to the left, the side that takes fewer moles of gas, so the CO2 goes down. Now, what I'd like you to do is to look for this other worksheet called Le Chatelier's Principle 2, and it's all set up as boxes. And what we're asking you to do is to go through, this is all about this same equation up here. For each one, follow the things, decide whether there's too much or not enough of something, put in the shifty arrow, and then go through and say up or down or up or down. Now the last part here, we're asking here this from forward, is it going to change the KEQ value? We don't want the real KEQ value, just want to see is it going to change up or down. And just to let you know, the only thing that changes KEQ is temperature. The only thing that changes KEQ is temperature. All the other changes you make will even out, and you don't end up changing the KEQ. And the KEQ, remember, it's products over reactants, so whatever happens to the products, that is what's going to happen to the KEQ. So if you have a temperature change that increases NH3, then it's going to increase the KEQ. If you have a temperature change that reduces the NH3, then it's going to reduce the KEQ. So try this, and then we're going to talk. We're not going to go over the answers, so check with your neighbors on that. Now, because you've seen this process, okay, and that all those ones on that second worksheet are based on this equation, then this is one we want to look at and kind of apply what we've learned. Making NH3, that's a very, very, very useful thing to do, because for plants, for fertilizers, they need to get nitrogen from the air. But nitrogen molecules are extremely, extremely stable, and it has to do with the fact that there's a nitrogen-nitrogen triple bond, and it takes a lot of energy to break that. So most things cannot use nitrogen directly from the air. One example that they can is something like legumes, like beans and peas, because they have nodules and things like that. But that's a biology thing. So most things need fertilizer. So one of the beginning steps for this is to get some ammonia, and you can turn it into fertilizer, and it's a really important process. So a guy named Fritz Haber in Germany worked up a process for this using the same ideas that we have been doing. So you've learned that if we increase the amount of NH3, increase the amount of N2 gas, okay, increase its pressure, that will shift the reaction to the right. Okay, another thing, if we increase the amount of H2 gas, okay, that will also shift it to the right. We can also see that because it's 4 moles of gas on this side and only 2 moles of gas on this side, if we increase the pressure, reduce the volume, that will shift the reaction to the right. Now, two other things. One is we say, well, what if we remove NH3? If we were to take away some NH3, that would help shift the reaction to the right. And the reason we can do this is N2 and H2, okay, those are both nonpolar molecules, diatomic nonpolar molecules, so they have very weak intermolecular forces. Whereas NH3, since it's pyramidal, trigonal pyramidal, then it is kind of polar. It's got a negative end and a positive end. In fact, we should recognize that that has hydrogen bonding, so significant intermolecular forces. So if you start cooling this down, the whole process down, we find out that the NH3, you can liquefy this relatively easily. And if you can liquefy it, you can remove it from the reaction mixture. And then we can reuse the nitrogen and the hydrogen. Okay, now the other part is temperature. If you were to go through this and say, okay, what can you do to the temperature to shift this to the right, then the idea is cool it down. And if you cool the reaction, you're removing heat, and that'll shift the reaction to the right. The problem with that is that also slows down the reaction significantly. So what Haber figured out is, let's go ahead and do this at a high temperature, because even though that actually is going to shift the reaction to the left, it'll just get to our products, okay, more quickly. So that speeds up the reaction, and then as we remove the NH3, we can just keep removing it, make some more, keep removing it, make some more. The other thing was to go through and find a catalyst, and it turns out iron works pretty well as a catalyst for this reaction. So the whole Haber process is use a lot of N2, use a lot of H2, remove the NH3 as it's formed, run it at a relatively high temperature so that it will react quickly and with this catalyst. But if you keep removing this ammonia all the time, then that increases the yield of the reaction. You make lots and lots of ammonia. And that is a useful process called the Haber process. Now looking kind of at a schematic of how this is done, you can see they put in hydrogen and nitrogen gas into the reaction chamber. Here's our catalyst. Okay, this is our iron catalyst. and that causes it to make a little bit of NH3. Now you take this and you want to heat it up in order to speed up the reaction. You run this through a heat exchanger so it'll lose some of the energy, cool it down, and then have a nice cool condenser, and what happens is the NH3 turns into a liquid, and you can totally remove it and keep that, and that's stuff you can use later. Now if you remove the NH3, that means we have nitrogen and hydrogen left over, so that can be put back in, warmed up again, and put back into the reaction vessel. So the N2 and H2 go back in along as the initial stuff we have, and the reaction happens over and over. So you keep the reaction going by keep feeding in N2 and H2 and removing the NH3. You've got a catalyst and you've got high temperature to make the reaction go more quickly, and that's the Haber process.